So here's an example of the sort of question you might get on a GCSE style exam paper. In fact, this is a genuine GCSE exam question, and it goes like this. The sketch, that's over here on the right, the sketch shows the graph of y equals sine x for values of x between 0 and 360 degrees. Okay, so there we are. You're given, so you don't have to use a calculator, you're given that sine of 70 degrees, the sine of 70 degrees is 0.9397. And that makes sense because we ought to know that the sine of 90 degrees is 1. So it's just shy of 1, so that's almost at the turning point at sine equals 70 degrees. So the question says, write down another solution of the equation sine x equals 0.9397, another solution. Okay, so that's going to involve us looking at the inverse sine function, or the arc sine. And then it says for part B, solve the equation sine x equals minus 0.9397 for the same range. And it's giving us two answers here, so there's 2 marks for this one because it's expecting 2 answers here for that range. Okay, so that gives us a bit of a clue. In part C, it says we have to sketch a graph of our own, okay, between 0 and 360 degrees for y equals sine of 2x. So it's going to, so a small transformation has taken place on the standard parent function. And in part D, we have hence, so you do have to use the information from this graph. Write down the 4 solutions of the equation sine 2x equals 0.9397. So those numbers again. And we're given 4 answers here. So this question has available a total of 8 marks. Okay, does that make sense? Yes, because this one is, so the sketch is worth 2, but we get a wonderful amount of marks for this last problem. So really we're hoping that for part D we're going to get everything right. So a lot of opportunity to pick up marks here. Now the examiner's remarks say this: parts A and B were done quite well. Good. Okay. Although 430 wasn't uncommon in part A. Now we'll come to that. Why did people write down 430? Although they say and was correct. So 430 degrees wasn't incorrect. So again we need to look at why would an answer which we might expect to be wrong actually given a mark. Anyway, that's good news. So people picked up a mark there. Answers of, for example, sine 110 degrees instead of 110 degrees were accepted. So there's a bit of leniency there. If they knew what you meant, then they gave you the credit that you were owed. Okay, part C, however, was done badly. This is the curve sketching. The most common error, they tell us, being drawing the graph of y equals 2 sine x instead of y equals sine of 2x. Okay. So, however, all wasn't lost because the mark scheme allowed follow through, an answer of theta plus 180 following an answer of theta earned a mark. So we'll have a look at that. Then they say it was quite common for candidates to pick up 5 or more marks on this question. So, you know, it's one of those questions that people are going to have a go at if they've got any sense and pick up quite a few marks. Good. The symmetry of the graph was being tested. So we'll have a look at that. And many candidates did understand this, so they acquitted themselves quite well. Okay. So this is a nice question. Plenty of opportunity for marks. Let's give it a go. Okay. So the first thing we want to do is, well, let's just have a look at it. You're given that sine of 70 degrees equals 0.9397. Now, if we have a look at this graph here, 70 degrees, so we've already said the sine of 90 here is 1. You can see that on the graph. 70 degrees is going to be, well, let's say about there, isn't it? Okay, so let's mark that on our graph here. Okay, so there's 70. And we know that the value then here, in other words, when you take that up to that point on the curve there, then draw that across. Okay. Then what they're saying is this value here on the y-axis is 0.9397. And that looks about right. It's just under 1. Okay. In fact, I've sort of drawn it even further down. If I'd have drawn it more accurately, it would look something like that. Okay, good. Now, what have we got to do? We've got to write down another solution of the equation sine of x equals 0.9397. And what that means is we're looking for the inverse sine of x, so sine of minus 1, and it doesn't mean to the power of minus 1, it just simply means the inverse or arc sine of x. So the arc sine of 0.9397 we've been told is 70 degrees. Okay. Now, what are we going to do to get a similar value? Well, if we've got 0.9397 along here, where does it hit the graph again? It hits it again here. Again, I've come down a bit too low, but it'll do. So we've got the sort of symmetrical around the 90 degree, the x equals 90 degree line will hit our x here at 100. Well, if that's 90 minus 20, then we've got 90 plus 20, which is going to give us 110. So we can say that the inverse sine of 0.9397 also equals 110. So our answer for part A is going to be 110 degrees, 110. Now, just before we move on, just to remember that some people did say 430. 400 and let's do it in a different colour. Okay, 430, and they did get that correct. Let's have a look. Let's use this colour here. So 430. So what was going on there? Well, if you subtract 360, in other words, 430 would be if you had the unit circle like this. So that's 360. If we keep going, then how far round do we go? Well, if we subtract 360 from 430, what do we get? We get 90. No, we don't. What am I talking about? We get 40 add 30, 70. Okay, just checking my maths here. 360 plus 70 gives me 430, so that's correct. I thought 90 had to be wrong. So 70 degrees is also 430 degrees. Okay, in other words, it comes round again up to this point here, which is also 70 degrees. So 70 degrees is also 430 degrees. Okay, and that's why they got the right mark, because it didn't say in this part that the answer needed to be within the range 0 to 360. Therefore, they were allowed that one mark. So still a little bit odd. What they needed to do was to get to 110. Okay. I guess what they did, actually, that makes sense, is they took that 70 and they simply added 360 and they got 430. So I think they struck lucky there. Anyway, 110 is the value that we were looking for. All right. So, part B. Solve the equation sine of x equals negative 0.9397 for values between 0 degrees and 360. So this time it really does stress the range. So what we've got is the same numbers as up here, but it's just in the negative now. So we'd expect it to be here on the graph, about there. Okay, and I don't know, it's going to be a bit hard to draw. That would map onto the y-axis there at minus 0.9397. Okay, let's just join it up to here. Now, if it hits the graph at this point here, if we look at the value on the x-axis, what have we got? Well, it's again got to be 270 minus 20, so we're going to have 250. 250 is where we get that negative value. And the other place we're going to get it, of course, is when we add 20. So it's going to be on the other side. So if we draw it down, again, there it is, hitting the curve at minus 0.9397. So 290 degrees at that point. So we've solved the equation. We don't really need to put any working out, so I'm just going to say C graph. And we can just straightforwardly fill in our answer. The answer in degrees is firstly 250 degrees and secondly 290. And that completes part B. Okay, so part C. Now in part C we're asked to sketch the graph of y equals sine 2x for values between 0 and 360, and they've given us the framework. So we can't choose where we put our axes. If we did, normally we might draw a period of minus 180 to 180, which is the sort of usual convention. But what we're going to do is use their framework. And the very first thing we want to do if we spot that we've got a transformation here is we want to check what the period is of that function, of that transformed function, you can say. Okay, so period, let's write it over here. Period, well, the period for a sine graph would normally be 360. But when you have a value, a coefficient of x, you could call it in front of the x here, then what you can say is that for every value of x that we're taking, for every point, every angle that we're going to read off, then it's going to be twice that angle. So you, as it were, going around the unit circle twice as fast. And if you're going twice as fast, then you're going to halve the period. So we're saying divide by 2 now will give us our period. So 360 divided by 2, 180. Okay, so what's going to happen is we're going to have a period between, if we start the drawing here, between 0 and 180. Let's just draw some dots on like this. That's going to be one period, and therefore our second period, so the same period, it's going to repeat. In other words, we'll come to 360 like that. Okay, so that's sorted out the periods. The next thing we've got to think about is the amplitude. Okay, now we're given a range of between 2 and minus 2. The question is that appropriate? Well, we've got an amplitude of 1. Okay, because there is no multiplier, if you like, of sine of 2x. In other words, if we multiplied by 1, that would give us the same value. So if the amplitude is going to be 1, then, okay, I'm going to say that my sketch is between, well, we want to go above and below with a sine graph, so it's going to be minus 0.5. Sorry, I should say amplitude equals 1 to start with. Okay, amplitude equals 1. And a common misconception actually is then to go between 1 and minus 1. But remember, if the amplitude is 1, like this, then the range that we want to draw it between is going to be between 1 and -1. Okay, so if the amplitude's 1, we have a range of -1 to, there we go, like this, to +1. So that sorts out the amplitude. So it's not going to go up to 2. It's only going to go halfway up this range that they've given us. Okay. Now, all we need to do is sketch our graph. Well, if we start with 0, the sine of 2 times 0 is the same as the sine of 0. So sine of 0 is 0. And so that's where we start our graph, at the origin. If we think of 90, then, well, normally at 90 we would have a y value of 1, but this time we've got a compressed value. So if I put my quarter values in here now, okay, so and imagine my sine graph going down and round like that, I'm going to have a value of 1, okay, and it is going to be 1 because I've got an amplitude of 1, so my value of 1 is going to be there. Okay, I can just draw a little curve on there straight away so I can see where it's going, little eyebrow. And down here, in other words, what would be, well, what would it normally be? It would normally be 90 add 45, 135. I'm going to, again, get a turning point like that. And all I need to do now is put a couple of dots here where I want to join up my graph. Okay, I could measure them out. That would be root 2 over 2. It's going to be roughly 0.7, but usually you just need these quarter values, and that gives you enough information to draw up quite a nice little sine curve here, I hope. Whoops, something like this. Okay, it's got a bit thick there, but it should be okay. Let's go down here, turning the corner here. There we go. Now, they don't want us to stop there, so we have to continue. So let's again use our quarter values, and about like that. If I do think of this as being 0.7, that's going to be about here and about here. There's my turning point. Draw some lines in. Crosses the x-axis there. And here, there's my turning point. Again, think of 0.7, that's going to be about there and about there. Draw some lines in. And then I just need to join these up. So go into here, around the corner to here. Whoops, I might get a little bit wobbly there. Let's just, there we go. I think that's good enough. I'm going to go through the 270 mark there, round the corner, and whoops, I'm going to correct that one because that got a little bit bendy. Let's just have another go at that. Okay, so round the corner, up, and completing the graph there. Okay, let's have a look. That looks okay. So we've now got our graph of y equals sine 2x. Okay, part D. It says hence, and all that means is, given the work that you've just done, you should be able to now find 4 solutions to the equation sine of 2x, equals 0.9397. Okay, so we've got that graph. But we've got y equals sine of 2x, but we're told that we have 0.9397 somewhere on that graph. Well, it's going to be here. Let's use a different colour. Okay, so that's where we've got a value of 1, and here. and -1 here and here. So I'm just going to mark those on my graph there. So where I've got there 0.937 is going to be here, so that's point A, let's call it. Here at point B, which ought to be just a little bit, there we go, somewhere around there. Okay, let's just draw where it hits the y-axis. So there's A and B. Now I don't want to go down here because this is a positive. Okay, so there's no negative in front of this. So we've got to stick to the positive values, which is where the graph is peaking. So I'm going to have another one here, that will be C, and another one here, that will be D. Okay, and again these will be read off on the y-axis. Okay, so that's found my 4 answers, and I'm actually going to label them A, B, C and D, and now all we need to do is calculate them. Alright, so what I've got here at my turning point is, not my turning point, at my quarter point is 45 degrees. So what is going to be the value of A? Well, when on this graph the turning point was at 90 degrees, I subtracted 20. So when it's at 45 degrees, I'm going to subtract half of 20, in other words 10. So my value for A, let's just do an arrow, must be 35. My value for B must be 45 plus 10, in other words 55. And here I've got the same sort of situation. I've got 180 degrees, between 180 degrees and 270 degrees, so that's 90 degrees between those two values. Okay, so half of 90 degrees is 45, so I've got, just go to one side here just to make sure we get this calculation correct. I've got 180 plus 45 is going to give me 225. Okay, now just to make sure that's correct, if I add 45 to 225, let's write it out again then, let's make that clear. Add 45, so this is an addition. It should come to 270. Well, 5 add 5 is 10. We're going to carry. 2 add 4 is 6, plus 1 is 7, and now 270. So that is the midpoint. If we weren't sure, our calculations have just made sure that we've got our sums right. So we've got a point of 225. Okay, so now our C and D points must be 10 either side, here and here. So in other words, 215 and 235. Okay, so we're ready now to fill in our values. A, we've discovered, is 35 degrees. B is 55 degrees. Let's put C graph again for our workings. So, sorry, C is 55 degrees, B is 55 degrees, C is 215, and D is 235. So, we should have got all of those answers correct. Really, we've done checking as we go along, but it all sounds pretty plausible. Our graphs really give us that check, and hopefully we've got the full 8 marks. Now, one final thing to mention while we're up on this part of the question. There's a very interesting thing that doesn't imply that, it's not really an issue for this exam question, but it's a very important point, and one that we should just dwell on, because there's something strange that went on here. What we said is the inverse sine function of 0.9397 is 70 degrees. And then we said, no, the inverse sine function of 0.9397 is 110 degrees. Well, which is it? A function, let's just use a different kind of pen again. A function is, if you remember, when you have a kind of machine, if you like. It could be, when we have a function like x squared plus x or something like that, then it's pretty straightforward and you can always reverse it. But there's something odd going on here. Now, what we're talking about with a function is inputting a value. So let's call that the input. And out comes another value, the output. So if we think of sine x equals 0.9397, what did we put into it? X. Okay. Then the sine function did its work. Let's write sine. And the output was a single value, in other words 0.9397. And that defines a function. You put one value in, you get another value out. So what happened here when we had an inverse sine function? We went, in other words, the other way. So we now input in this direction. Its output gives us two values. Exclamation mark, exclamation mark. Now that can't happen. In other words, to be defined as a function, to be a function, you just want to have one, you can only have one value coming out the other side. So we say that this, in fact, isn't an inverse sine function. It's not a function, even though we can calculate, using this graph, for example, we can calculate, as many values as we want. Now, if it's not a function, then that's going to give us a problem, for example, with the calculator. And you can try this out for yourself. If you put in 0.9397 and take the inverse sine function of 0.9397, you should get 70 degrees. But you'll get an error message if your input is 110 degrees. So what they've done to make it work on a calculator is they've limited the range of the angle that you can put in. It's all going to be fine up to 90 degrees, but if you take it above 90 degrees, then you're going to produce an error, and that ensures that there is only one output. That maintains the idea of a function. And in fact, otherwise, if a calculator started producing multiple entries, well, I don't know how you would display that. So they've limited the function to between 90 and, going in the opposite direction, minus 90. So in other words, the x is defined between minus 90, okay, and positive 90. And just to maintain the functionality of it, you might say, so that it just is going to produce one value for every one value that you put into it. Okay, so a little curiosity there, but I hope that makes sense.